When you write programs, which are these instructions for the computer to follow, you use a formal programming language. This ensures that the computer will not misinterpret what you mean. When we write code, we choose a formal programming language, and specifically, we choose a high-level language. These high-level languages are for us. We are able to read, write, parse, interpret. We can look at these programs, even if we don't know exactly what they're supposed to do, we can get a pretty good idea because it's written with abbreviations and things that we understand when we read it. An example of this would be Java. It is guaranteed to be unambiguous for the computer and yet still easy for us to understand, as opposed to a low-level language, which is not natural for humans at all. But unfortunately, the computer is only capable of understanding very low-level language, and the hardware itself needs specific instructions. It needs to be told which of my circuits need to get turned on and which of my circuits need to be turned off, and that is known as binary. We like to think of those ons and offs as ones and zeros. It makes it a little bit easier for us to understand. So when we've written our code in a high-level language, something needs to happen so that the computer can figure out what we meant. The word add doesn't mean anything to the computer. The word print doesn't mean anything to the computer, although they are easy for us to understand. And so some abstraction is involved that shields us from that low-level language, but ultimately that's what it has to end up as. So what that means is that our nice high-level code that we've written that makes sense to us has to be compiled. All right, and so there's a program that the computer will run when you want to have it show you what your program does, called a compiler. And it will take your high-level code or your source code, the code that you have written, the set of instructions that you wrote, and the compiler will translate them, convert them into a low-level language, ultimately into machine code. This is a quick example, not to scare you and not to confuse you, but just to show you that at the very lowest level, the computer needs zeros and ones. This is an example of, on the left, some binary code that the computer might be able to understand. Ultimately, what's going on here is we're trying to get the computer to be able to read through a list of numbers and to determine how many odd numbers and how many even numbers are in the list. And so the zeros and ones, we can read that even though we have nice little notes that tell us what this program was doing. If those notes weren't there, we would have absolutely no idea what was going on. On the right, we have something called assembly language, which is kind of a step up. But when you look at the bold-faced codes and characters, we can pick up a few things. I see the word add. That's good. I understand the word add. I see the word halt. But the rest of it, without those notes, I would still not have any idea what has happened. Obviously, there's a little bit more abstraction there because I can see words I understand, and I just said the computer doesn't know the word add. So more abstraction, but still very confusing. Now let's look at this in a high-level language. This is an example of a text-based language called Python, and it is doing the same thing. It is looking at a list of numbers and trying to determine how many odd numbers and how many even numbers are there. And really, even though maybe you have never seen Python before, you can look through these 10 lines of code and get a pretty good idea of what's going on. You can read, count odd, count even numbers, print, and I can predict what is going to show up on my screen based on these instructions. And this is much more easy for us to understand, even if you don't know programming. So those are some examples of some low-level binary and then semi-low-level assembly language as opposed to this very high-level Python code. Once you've written some code that your computer is going to be able to understand, then of course you want to run the program. And you want the processor, your computer, to be able to execute your program. And you may have heard that term before, an executable file. That just means that it's a file that's capable of being executed or run as a program on the computer. And when we break that process down a little bit, we look at the first step, which is to load instructions in raw data, any data that's required to run the program, into memory. which is called RAM. I'm sure you've heard that term before, RAM. RAM stands for Random Access Memory, and it consists of tiny electrical circuits used for storing information. So each individual circuit in RAM is capable of storing 1 bit of information. And I'm sure you've heard that term also, bit. You may not know that bit is actually a combination of binary and digit. Binary digit, and that contracts into the word bit. And bit means one individual circuit, either 1 or 0, one tiny piece of information. So to give you a little bit of perspective on that, if you think of 1 gigabyte of RAM, which we all know that many computers have much, much more than that, but 1 gigabyte is actually more than 8.5 trillion bits, individual circuits. So that's a lot of information that RAM is capable of handling. This information is loaded from the primary storage of the computer, so the main storage or the memory that stores data for quick access. And for long-term storage, we use our secondary storage, so it's an external or auxiliary memory, such as a flash drive, such as a hard drive, or something like that. And that set of instructions is now loaded into RAM where it needs to be. And the next step is that the central processing unit will read and execute the instructions. The CPU, or the central processing unit, is often compared to the brain of the computer. So it's where all of the calculations and different operations are going to take place. The CPU reads each and every one of those tiny bits one at a time, and it executes each instruction that the code or algorithm specifies. So as the CPU reads the program, each instruction or operation causes different components to be activated throughout the computer. For example, maybe some actual mathematical or logical calculation has to take place. And because of those calculations, there are new values to store. Or maybe something has to be drawn on the screen or shown on the screen. Maybe the computer has to know which button the user clicked on in order to run the program or send data, for example, to a printer, or output music or sound effects. A lot of other things in terms of basic computational functionality. And all of these different things make up what the user sees when the program runs. All of it came from the original data and the original code. So we talked about how RAM holds, trillions of bits of information, and the CPU actually executes these one little bit at a time. And it seems like that would take a long time. Well, that's trillions of bits to go through, and the CPU is looking at them one at a time. But that is actually not the case. The processor has kind of an internal metronome that sets the pace of instructions that are executed per second, and that's known as clock speed. So, for example, if you have a 2.8 gigahertz processor, you're looking at a processor capable of executing 2.8 billion instructions per second. And that actually would be a fairly lower level processor. Computers today have much higher level processors, multiple processors. And because of that, we understand that a lot of times the CPU is really doing nothing. It's just waiting for more instructions because of how quickly it's capable of handling them.